was concerned. Everyone was hiding on me. No one else here.
Excuse me, I forgot my book.
Yep. Anyone do anything fun or interesting? Fun, interesting? No? No one does anything fun or interesting anymore. We're a group of unfun, uninteresting people. You don't go home. Okay, you just live here. You just hang out in the court? Oh, you don't get to go home. Or you only get, you're stuck here all day? All week? All night? You don't get to go home at all? I know that routine. I know the challenges of trying to be really excited that you have the option of working from home and then realizing that the expectation then is that, yeah, that you are always accessible. And I remember when bothering my first boss for BlackBerry, and really this was in circa 2005, like they were still cool and thanking my boss for one, and he finally relented. And then clients figured out that they could email me at all times and I would respond. And my girlfriend at the time referred to it as my little baby. It would cry and I would go running. So yes, and now at the law firm I work at, I had an incident where I didn't get an email, and it was because I wasn't getting an email on my phone, and then I was like, oh crap. Now I can email my phone, I have remote access, and I do have the managing partner emailing me last night at 11 o'clock.
And you still have fun.
And I still have no phone.
Oh, no fun.
No fun.
I thought you have a fun.
I have a phone, but I don't think I have any fun. Okay, so last class we actually had some fun, right? So we ate some Subway sandwiches, right? And what was the point of eating those Subway sandwiches? Well, the point was to be able to determine if Subway was lying when they sell their sandwiches as a foot long, right? And we said that the reason that the way you would test that if you were to go to court would be you would collect some data, which we did. You would determine some statistics based on your data. So you might look at the mean, or you might look at the standard deviation, but the mean is really what we're concerned about. And then you would want to be able to say, hey, do we have enough evidence to say that Subway is lying when they advertise their $5 foot longs of little dance, saying that the sandwiches are less than 12 inches, like those two guys in Aldridge said. And we can actually look at your data. There's your data. And we see that the average is actually 11.68. So the average, the mean, based upon the 10 sandwiches, so yours and your 9 friends, and I actually got a sandwich, was that the mean was 11.6875 of you measuring your own sandwich, and measuring your friend's sandwich, we got a little bit higher mean of 11.775. So the difference between your measurement and your friend's measurement of your sandwich is attributable to what source of variation? No, remember what we did, right?
Yeah.
So you measured your sandwich, and then your friend measured your sandwich, right? Same tape measure, same sandwich. Different person, but you and your friend were the same, right? So the question was, what word characterizes the variation that we see between your measurement of your sandwich and your friend's measurement of your sandwich? Starts with R. We talked about it when we talked about our gauge R&R studies, right? And the reason we do a gauge R&R study is to yeah, those are the words I'm talking about. Those are the two words. So I'm talking about repeatability and reproducibility. But the reason we do a gauge R&R study is to understand the sources of the variation that are attributable to the parts, so the differences between the sandwiches. So then there's the variation that's due to the measurement system, the machine, the tape measure. And then there's the measurement that's due to different operators. So between our column B and our column C here, between your measurement of your sandwich and your friend's measurement of your sandwich, well, what type of variation is that? That's the variation that's due to reproducibility, right? And the way to remember that is people reproduce. So we'll be coming back to this data in a bit, when we actually are going to perform the hypothesis test, the t-test, to determine if Subway is lying. And then we'll come back to this probably next class And we'll use the paired t-test to determine if there's a statistically significant difference between your measurements of your sandwich and your friend's measurement of your sandwich. And just as a coming attraction after that, you will get the week after that, you will get the tri-term, the third exam that you'll be taking. Yes, I know, it's getting exam time. We've only got, what, 11 weeks until the exam? 12 weeks until the real exam? So time is going to be an issue. So you'll have 2 weeks to take the test, and then we'll go over it. One of those weeks I will be away. I will be in the UK and France. Sorry. But then we'll come back, we'll go over it, and then after that we'll actually do the Oreo exercise when we'll be able to answer if double stuffed Oreos are really double stuffed. This is a little bit of a coming attraction. So this is one of the most important decision trees that you're going to see. So the other really important one where I emphasized it was really important to be familiar with was the decision tree for control charts, right? Remembering that lovely page that I said, Dancing Girls, Bright Lights, be familiar with. So the other one of those is the hypothesis testing. So we can use this to determine what we're testing. So we can test for the mean. We can test for the proportion. We can test for the variance. We can also test for goodness of fit. Goodness of fit being how well does my mathematical model describe what I've observed. So when we're talking about the means, we need to figure out how many samples we have. Are we dealing with one sample and we're comparing that to a standard? Are we comparing two samples? So are we comparing the length of Subway sandwiches from Eatontown to the length of Subway footlong sandwiches from Camden? That's two samples. Or are we dealing with two or more samples? Are we dealing with the length of Subway sandwiches from Camden, New Brunswick, and Eatontown? And that would be the case of two or more samples. So if we're dealing with one sample, we're going to either use the Z or the T test. If we're using two samples, we're going to use a form of the t-test, and then we need to determine if we have equal variance or unequal variance. And then if we're dealing with two or more, we're going to use ANOVA, which stands for Analysis of Variance. So we talked about how there's a null and alternate hypothesis. The null is what you assume to be true. The alternate is what you want to prove. So the null hypothesis in our Subway footlong example is what? What's our null hypothesis? Yep. Oh, what? Units are important, but yes, that our null hypothesis is that the Subway footlong sandwich is 12 inches. So our null hypothesis is mu, the average, equals 12. What's our alternate hypothesis? The thing that we want to prove. Yeah, that the mean is less than 12 inches. Okay, so we have our level of significance, alpha. Remembering that alpha is 5%, generally. Why? Because you have 5 fingers. Alpha, 5%. Because we generally are operating at the 95% confidence level. And we remember that 1 minus our confidence level gives us our level of significance, alpha. And alpha represents the probability of a type 1 error. Remembering the O.J. Simpson's example of what type of error? Type 1 or type 2?
He actually did.
Yeah, he did it, and the jury said he didn't. So we're in the bottom right.
It's beta.
Beta. Type 2 error. Very good. So our level of significance is generally 5%. But as I talked about with the criminal justice system, we set it even lower. We make it a really low level of significance. So we want to make sure that if we say there's a difference, there really is. We're really certain there is a difference. So if we have a smaller level of significance, when we say there's a difference, we're really confident that there is in fact a difference. Our beta risk is the O.J. Simpson type risk. And we're remembering that power is 1 minus beta. Kind of a definition. As you saw a question on that, I think it was in the pretest. So we have the p-value. So the p-value is what we use to determine if we're going with the null hypothesis or the alternate hypothesis. It basically tells you how likely it is of getting your data, the data that you've collected, if your null hypothesis was true. So if you get a really low p-value, that means it's really unlikely that you would have gotten your data if your null hypothesis was true. So given your data, given the measurements for Subway sandwiches that we have had in the Excel spreadsheet, how likely is it to have gotten that data if Subway was really telling the truth and that the Subway foot-long sandwiches were actually 12 inches? So that's your p-value. Okay, remembering this, so in the criminal justice system, our null hypothesis is the defendant is innocent. What we want to prove, our alternate hypothesis, is the defendant is guilty. And our level of significance is really, really small in criminal justice, right? It's beyond a reasonable doubt, really high standard for the government to be able to show that the government to be able to prove before we put someone in jail, because we're really concerned about the possibility of putting an innocent guy in jail. Yet every prisoner will always say they're innocent and they're in jail. Says every defense attorney ever, well, every prosecutor ever. Okay, so one tail versus two tail, right? So in our hypothesis test, we can have one of three different types of alternate hypotheses. The first of which being not equal to. So if we want to say if there's a difference or there's not a difference. It either is 12 inches or it's not 12 inches. That's an example of a two-tailed test. But that's not what we're concerned about in the Subway example. In the Subway example, we're more concerned about it being less than. We don't really care if it's greater than, right? If you get an extra quarter of an inch on your sandwich, you're happy. Get a little less than your 12 inches, well, depending on who you are, you might be a little annoyed. But, so if we're doing it the one-tailed test, our rejection region is on one side. So we want that area to be 5%. Whereas if we're in a two-tailed test, there's two rejection regions. It can either be off because it's less than, or it can be different because it's greater than. Okay, so there's lots of different flavors of testing. Going through this a little fast because we went through it before. So there's the z-test, the t-test, the paired t-test. And remembering that we use the paired t-test when we have two samples and there's some connection between the first sample and the second sample. So it was the same physical sandwich that got measured multiple times. So it wasn't a random sample. So we use a paired t-test in that case. If you were looking at individuals' weight loss and you had them weigh in today, and then you put them through some treatment, and then you weigh them in 6 weeks from now, they're still the same individual. It's not a random sample. So you use the paired t-test then. Okay, so the process is you determine the critical value from the tables. So this is about where we got up to last class, right? Oh, we got all the way up there? Cool. So we're just remembering how to read the t-tests, the tables for the z. So the first column represents the first decimal point, so 1.9, and then the second decimal point is on the top. So for the z alpha over 2, where alpha is 5%, so at a 95% confidence level, we find that z alpha over 2 is 1.96. If we wanted to go down to the 99% confidence level, so alpha equals 1, we would find the z alpha over 2 value to be 2.57. Fortunately for your exam and for real life, we generally are operating at the 95% confidence level. Alpha equals 5%. That's for the two-tail test, so we're doing z alpha over 2. For the one-tail test, it's similar. So if we're dealing with an alternate hypothesis of less than or greater than, we'd be on the one-tail test. So we can see that for our 95% confidence level, alpha equals 5%, the value is 1.645. Yep, 1.645. If you 1.64 is perfect fine. Okay, then we get the t-test, the t-table, which we use in the t-test. The t-table is a little bit different to read. We need to know our degrees of freedom. So we need to know what our sample size is. Our degrees of freedom is equal to 1 minus our sample size. So we had 10 sandwiches that we measured, right? What's our degrees of freedom? 9. There we go. N minus 1, so 9. So the first column represents your degrees of freedom. So for our Subway sandwiches, we would be on the 9 level. And then the top row represents the tail probability, so alpha. So we'll go back to this table and we actually calculate out if there's a statistically significant difference with our sandwiches.
Can you go back one
Yep.
slide, or two more? This one for two-tail, why do I have, and I think I have it backwards, I said it's always greater than or equal to, I mean, greater than or less than test, isn't it supposed to be that it does not equal? Like a two-tail test is always for questions?
These are all for questions. So the difference is what the alternate hypothesis is. So in the case of the two-tail test, there's a rejection region that's greater than, and there's a rejection region that's less than, because your alternate is not equal to.
Okay.
In the case of the one-tail test, you only have a rejection region that's greater than, or a rejection region that's less than.
In the two-tail?
In the two-tail, there's always two rejection regions. There's one less than, because you can be greater than, or you can be less than. So there's two rejection regions in the case of the two-tail test, because your alternate hypothesis does not equal.
Okay.
And in the one-tail test, you're only concerned with one side. Is the mean less than 12 inches? So you're only dealing with a one-tail test. So that's less than, or equal.
Okay.
So then we come over to the t-test. So the t-test gives us the area based upon our sample size. So we use the t-test and the t-table when we're meeting the queen. Come on, you know the deal. You don't have to laugh, but you at least have to give me evil looks to make sure that you're paying attention. What T, the queen?
I didn't know that.
She did.
That's fine.
She did it. I got one evil look for that. So we use the t-test. So we use the t-table and the t-test when we have a relatively small sample size. And remember, whenever you're at a bar drinking Guinness, the guy Gossett was actually an engineer for Guinness. And the reason he came up with this is that Guinness gets their barley from all over the world, and it's really expensive to ship big batches of barley around the world. So Guinness had to come up with a way of determining what barley to use in their beer without having to ship these container loads around the world. So that's how the t-test was born. So next time you're at a bar and someone orders Guinness, well, you can mention the t-test and the t-distribution. And you'll probably have an empty seat next to you. We might have something to add to my Ishikawa fishbone diagram. Okay, so we have the F table. The F table is used for the F test. So you have to know your degrees of freedom of the numerator and your degrees of freedom of the denominator. So the degrees of freedom of the numerator are on the top row. The degrees of freedom of the denominator are on the first column. And we'll walk through that when we get to the F test. So we're up to the Z test. The Z-test is very similar to the t-test, and we use the Z-test when we have a very large sample size. So what do we need to know? Well, we need to know our null hypothesis, right, and our alternate hypothesis. So in our null hypothesis, we have a standard, and we want to compare that standard to what our data says. So our null hypothesis says that mu equals something. Right? And from our data, we can calculate what our average is. From our data, we can also calculate out what the standard deviation is. And we know how large our sample is, so we can know n. So then we just need to calculate out what z is. So how do we interpret this? That's the more important question. So it depends what our alternate hypothesis is. And the easiest way to do this is to draw a picture and to label the picture HO, HA. And the critical value determines the transition point from HO to HA. So if we're at the 95% confidence level, we have a minus 1.96 and a 1.96. So if we get a value of 2, do we go with our null or alternate hypothesis? If we were to plot 2 on this graph, so it goes from 0 to a big number over here. If we were to get the value of 2, are we in the pink region or are we in the black region? Come on, guys. Is 2 greater than 1.96? Okay, so if we plotted it, it would be in the pink region, right? So would we go with our null or alternate hypothesis? Alternate. The pink is the alternate. There we go. Sometimes they are that easy. Okay, what if I got a value of minus 3? null, or alternate. So if we plotted it, -3 would be somewhere about where the red dot is, right? Is that in the pink region or the black region? Pink. There we go. So the pink means we go with the alternate. Good. And if we got a value of 1, we're in the black region, right? So we would go with our HO, or null hypothesis. Good. That's if we're dealing with a two-tailed test. So if we're doing with a one-tailed test, if I got a value of 2, we would go with the alternate, right? If we went with 2, right? 2, we would plot it somewhere around there. And that's clearly in the pink region, right? What if we got a value of -2? HO or HI? HO, right? If we got a value of -2, we would be somewhere over here. And we would be in the, well, not necessarily the good region, but the HO region. Actually, as a practical matter, you're generally have a problem when you're in the HO region because you want to prove the alternate to be true. And if you run your test and you are unable to reject your null hypothesis, you generally have nothing to report on. Okay, so I didn't grade your midterms, and we're kind of running a little bit behind, but you can see how to walk through these calculations. Now we're up to the t-distribution. So the t-distribution is used in the case when we have a relatively small sample size. What's a relatively small sample size? Generally greater than, less than 30. After 30, the t-test, the t-distribution, and the z normal distribution become essentially the same. They converge.
I thought you said before we use the t-distribution for a large sample.
T is used for small. Z is used for large. If I said it backwards, I apologize.
Small is the t, and which one? The
Z is for large.
T is for large.
T is for
Small.
Small, okay.
Z is for large.
Okay.
So there's different flavors of tea. Some people like green tea, some people like black tea, some people like herbal tea, some people like white tea. Yeah, okay, sorry. So there's the one sample T. So the one sample T is like the one sample Z, where you have a standard and you want to compare it to your sample. Then there's the two sample T. So that's when you compare one sample to another. Then there's the pair T, when you're comparing two or more dependent means. Okay, some assumptions. These are mathematically interesting, not practically interesting. The observations must be independent. Well, what does that mean? That means if I observe one sandwich, it doesn't affect the observations of other sandwiches. So a lot of times, your independence assumption is violated, particularly in manufacturing. So if you observe a small part coming off your production line, does that affect the probability of observing the next part being small coming off your production line? Yeah, it depends. It depends, right? Your intuition would be that it's more likely that the next one coming off the line might be small too, because there might be some sort of systematic problem that's causing you to produce small pieces. Whereas if I flip coins, I get a heads, does that affect the probability of getting a heads the next time? No. Or if I got a sandwich from Subway, and I got another sandwich from Subway, does the fact that the first sandwich was small affect the probability that the second sandwich is going to be small? No, they're independent.
I don't understand that, because if it's a machine, it's the same person, then the second sandwich could be small too, but it's the same person making it.
Yeah, exactly.
So you just said it's not.
I'm saying what I was trying to say is that, yes, if there was some sort of manufacturing defect that was causing the Subway sandwiches to be a different size. But what we had posited before was that what was really affecting the bread size was all these random environmental factors, the pressure, et cetera. They were always putting in the same amount, and it was some sort of random variation that was causing there to be this differences in what the bread came out to be. And we were trying to prove that there was some sort of systematic reason for the sandwiches being less than. But what I was saying in this case is that there's no compelling reason for why, if I got a wheat bread sandwich and I got an Italian sandwich, why those two breads would have anything to do with each other. Or if I got a sandwich today, why that would necessarily impact the sandwich tomorrow. But if I were to observe that I had a defective part because the machine had malfunctioned, it's more likely that that malfunction is going to continue on in the prior part. Does that answer your question?
Sure.
Okay. The two underlying populations must be normal. That's actually a pretty good assumption. And the two populations from which the samples are selected must have equal variance. Not a big deal. So we have the formula. Anyone think that formula looks a little familiar? Yeah, so we have two noticeable differences between the z-test and the t-test. Can anyone notice any of them?
It is, yeah, sigma.
Yeah, we have a sigma instead of an S, and there's one other really obvious one. It says T. The other one said Z. Okay. So we have our T distribution table. And we have our formula, right? And we have some data. So based upon column 1's data, which is the measurements of your sandwich, M1, do we have enough evidence to say that Subway is lying? I don't know.
No.
How would you do it? How are you going to do it? Let me say it that way. Well, you do, right? You do have enough data. You have data. You have 10 observations, right? Well, let's write out what our null hypothesis is. So what's our null hypothesis? Okay, so what's our null hypothesis? Our null hypothesis is HO mu equals, oh, what's our alternate hypothesis? Yep, mu less than 12, right? Cool. Okay, so what does our procedure say? Then we need to determine what test we're going to use. What test are we going to use? Can you read that? Or
Less than 30.
T.
T. Okay, so we're going to use the t-test. So what's the formula for the t-test? T equals x bar minus mu over s over the square root of n, right? No, there's 10.
No. I think you are the only 8.
Yes, but you're night friends.
That's why the data is 10. It's 10.
It's 10. So it's there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Your number. And you can see who ordered which sandwich. Right? The sandwiches have names. Okay. So what's our level of significance? We're going to go at alpha equals 5%. That seems kind of reasonable, right? So alpha equals 0.05. N equals 10. What's that make our degrees of freedom? Yeah. N minus 1. So that's okay. So is this a one-tail or a two-tail test? Okay. So what's our T critical value? Nope, that's if it was a z-test. We're doing
1.64. Right?
Nope, that's if we were doing a z-test. We're doing it with the t-test. We need to go based on the t distribution. Okay, so we need to read down for our degrees of freedom from column 1. Our degrees of freedom is 9. And we're doing it for one-tail test, so we're looking for 0.05, our level of significance. So we read across, and we get our t critical to be yep, 1.833. Does everyone see what it is? Yeah, so what we're doing is we're going down to our degrees of freedom, which is our sample size minus 1, And then we're reading across until the top row has our alpha, our level of significance. And we see that is 9, 1.833.
So what did you put in for, I can't read what your pens, no offense, things.
Now, let me rewrite it with the green. Can you read the green?
I can read the green one,
Okay,
yeah.
let me just rewrite everything then. So mu equals 12. Our alternate is mu is less than 12. Alpha, our level of significance, is 5%. N, our sample size is 10, which means our degrees of freedom, BF, is n minus 1, which is 9. So then we're looking for T critical. Yep. Which is T of 0.05 for 9. So that's 1.833. Right? Cool.
What does that last one say? Your what? Equals 1 point? What did you have?
T critical, the critical value from the
Okay.
table. And that's for 0.05 and degrees of freedom 9.
Okay.
Okay, so to do the t-test, we need to calculate our test statistic. So the formula gives us the t-test statistic, t-test, equals x bar, our average, minus mu, over our standard deviation over the square root of n. Okay, so we need to know x bar. Okay, put the data back on. So x bar equals 11.6875. Our standard deviation is the point. Yep. So is this the standard deviation of a sample, or is this the standard deviation of a population?
Where'd you get S equals 3 point whatever?
From Excel. Yeah. Well, you don't have to cheat. You can buy the TI 36X Pro and just put in the data and hit enter, and it will give you the standard deviation.
We'll get that one problem off.
Yeah. What they would do on the exam, if they were to give you a hypothesis test question, is they would give you the standard deviation. It's kind of like it's given up there and ask you to calculate that.
Oh,
So they wouldn't give you a data set.
okay.
Okay, so we know x bar. Do we know mu?
Yeah.
12, right?
12.
Oh, yeah, mu is that.
We know s. We know the square root of n. Well, do we know n?
Yeah.
I mean 10.
9.
Okay. But no,
No.
degrees of freedom is 9. N is 10.
Yes, 10 is 10, number of samples.
Yep. So
Okay, n is 10.
that t-test equals 11.6875 minus 12 over 0.3498 over the square root of 10. Anyone going behind the calculator that for me? Okay, so always helpful to draw the picture. So we got our T critical value of 1.8. You don't have to calculate out anything.
We already calculated.
I give you everything. So we have our T critical value, right? Is that going to be on the left side or the right side? On the left side, right? Because we're dealing with less than. Okay, our T critical value was 1.8333. So if we get a value as extreme or more extreme on the green region, we go with HA. If we're in the white region, we go with HR. Yes. So negative 2.8 is somewhere over there. So that's our t-test. And that's our t-critical. Okay, so what's our conclusion? Yeah, which means what? What's the conclusion?
It means the null hypothesis is, we have to reject the null hypothesis.
Okay, continue. What's that mean?
It means the other way is true. It means
Well, it doesn't quite mean the other way is true, but
Means that you're gonna get a sub less than 12.
null hypothesis is not reject no, you reject, so that means that part is right. Let's go back to it.
okay, let's make it really simple. Do we have evidence to suggest that Subway is lying?
Yeah.
Yeah, we do. We have sufficient evidence to reject our null hypothesis. We have evidence to suggest that Subway is really selling sandwiches that are less than 12 inches. Kind of interesting. And that was only based upon 10 observations. Does the hypothesis tell us how big the difference is? No, it doesn't tell you. It doesn't tell you the magnitude. It just tells you, is there a statistically significant difference? So was it very likely for us to observe these 10 data points if Subway was really telling the truth that their sandwiches are 12 inches? So it's unlikely that we would get our data if Subway were telling the truth. But we don't know if the real mean would be 11.8, 11.9. Hypothesis test doesn't tell us the magnitude of the difference. It just tells us the presence of the difference. So yeah, Subway is lying. So those two guys from Oldbridge that sued Subway might have had a point. Everyone see why that is? Getting some blank looks, I'm a little concerned. It's just because it's a Wednesday and it's cold out? Okay, what did we do procedurally here? We determined what we were testing. We were testing the means. We collected some data. We then determined to use the t-test, the one sample t-test, because we were comparing a known standard to our data. We used the t-test because we had a relatively small sample size, only 10 observations. We determined our alternate hypothesis to be less than, because we were only concerned if the sandwiches were less than 12 inches. We then went to the table. Based upon our numbers of degrees of freedom, we determined what our critical value was. Then we calculated out our t-test, our test statistic. That was putting the numbers into the formula. Then we compared our test statistic to our critical value to say how likely was it for us to have observed our data. So when we drew the picture, we saw that was pretty unlikely to have observed our data if our null hypothesis were true, if the sandwiches were really 12 inches long. Kind of neat. Or am I the only one that thinks it's neat? What's with the blank stares today, guys?
I think we are just, accordingly, I am like falling off to decide what page it is,
Okay.
right or left, and how do you decide that?
Okay, I decided that because of what we were physically talking about, because we were doing it less than. If we were,
Yeah, okay.
because our alternate hypothesis was less than means we're concerned with the region to the left, the smaller stuff. If we had been concerned with greater than, we would be dealing with the stuff to the right, the bigger stuff. That's why we were only on the left-hand side. And that's why drawing the picture is important, because the picture shows you the physicality of, hey, we're only dealing with we want to prove that our sandwiches are less than 12 inches, so it should be on the left-hand side. Any other questions related to this stuff? I know it's not the world's most intuitive. So somebody was lying to us. Anyone want to go see Subway now? Anyone want to go walk into the one in on West Park and say, hey, I want my free sandwich? No one? No takers on that? Why not? You've shown that they're lying. Demand your free inch of a sandwich. Procedurally, everyone's okay with what we did and why we did it. and how to draw the conclusion. So the conclusion is the hard part, and drawing the picture helps. Drawing the picture allows you to have that intuitive sense of, am I in the HO region or am I in the HA region? So the HO region means that I did not find enough of a difference to say there is a difference. The fact that I didn't find it doesn't mean it's not there. It just means I didn't find it. So I'm going to stay with my null hypothesis. I didn't prove that the alternate hypothesis was true. But if I'm in the shaded region, the HA region, I did find enough evidence to say it's really unlikely that if what I thought was true is actually true, that I would have gotten my data. So if you're in the white region, you go with HO. Shaded region, go with HA. Draw the picture. It makes it graphically pretty easy to understand. Well, easier to understand. When reading the t-table, you need to know the degrees of freedom, which is always n-1. And you need to know alpha, your level of significance. And to know if you're doing a one-tail or two-tail test. And that's determined by what your alternate is. Your alternate hypothesis determining, are you concerned with greater than, less than, or not equal to? Not equal to being the two-tail test. Cool? Coolish? Okay. So how do you determine the critical value for chi-squared? So chi-squared is a little bit more complicated than what I've been using. We use chi-squared for goodness of fit. The easiest way is with the inverse function or the chi-square table. Okay. Let's do an example for the chi-squared test. Let's do that. How much time do we have? 15 minutes? Let's come back to the chi-squared test next class, just so we can keep moving. So we'll come back to chi-squared next class. So let's go to the F test. Anyone remember what to use the F test for? Anyone? What's the F test used for? Okay. Or you can just read what it says in the slide. That's too easy. Is test to determine if there's a significant difference between the variance? Do you think if you can use this to determine if there's a statistically significant difference between the variance, you could also use it to test this difference between the standard deviation? Yeah, because what's the relationship between the variance and the standard deviation? Yeah, the square root of the variance is the standard deviation. Yes, yes, the exam will try to trick you up every which way on that. So get it in your head to know the relationship between the standard deviation and the variance. Who's after me? So we use the F test. It's a ratio of our standard deviation from one sample to our standard deviation of our other sample. And the F test allows us to say, is it likely to have seen this ratio if our sample standard deviation from both samples were the same? So it always has the larger standard deviation on the top and the smaller on the bottom. Cool with that? So when would you use the F test? Yeah, when the variance is involved. So when would you likely use a hypothesis test to determine if the variances are different? Why would we want to? Why do we care about the variance? What does the variance measure? The variation. Yeah. Okay. Why do we care about the variation? It's an S. Yeah. Repeatability and reproducibility, absolutely. That's where we're trying to put a numerical value, assign the value to what our variation is, absolutely. But why do we care about it in general? Why does it matter how much our values change? Yeah, so it relates, so we know when we're doing process capability, right, we're looking at the ratio of the customer specifications, the upper and lower spec limits to the voice of the process, so sigma. So absolutely, if I have a bigger variation there, we're going to have lower process capability. That's one way, yeah, absolutely. You were saying?
Yeah, I was saying. process.
Yeah,
To
so,
determine the process capability, kind of establish
Mhm.
is proving or is complying with the customers' needs or whatever our specs.
Yep.
So,
yeah, and if we get back to even more basic, we remember that in lean, variation is a source of waste. It's a form of muda.
yeah.
So, because what variation is it means that any given part is more different than the average. And the more variation that we have, the harder it is to plan, the harder it is to predict. So if we have less variation, we can make better predictions. We can make better predictions when making statements to our customer that we will provide a good or a service that's going to meet or exceed your expectations. Or if we want to produce parts that are within our spec limits. If we have less variation, we'll be more likely to produce parts that are within our spec limits. So one of the most common times you use the F-test is you do a continuous improvement project to reduce the variation in some physical characteristic of your product. So you have your before, your baseline data. You then run your continuous improvement project. After the project, you collect new data. And you want to be able to say, hey, we actually did something. We decreased the variation. And was the decrease in the variation statistically significant? If not, well, your project might not have been successful. Remembering that up to 70% of all continuous improvement projects fail. So that's when you often would use the F-test to determine if you actually did decrease the variation. Let's go back to our subway data for a second. Well, probably for more than a second. So we have our data here. We have two measurements, right? We have the measurements of sandwich 1 and the measurement of sandwich 2. Do you think it's reasonable to compare the variation of measurements 1 to measurements 2? And it would be a pretty reasonable hypothesis test to question if the variations were equal. I think that's a reasonable question. So how do we do that?
The standard deviation.
Yep. So we need to know the standard deviation of each one. Okay. How do we do? So now we have the standard deviation of both your measurement, M1, and the measurement of your friend, M2, your colleague.
But isn't that the standard deviation of all of those? Don't you have to do the standard deviation of each one? You're doing the standard deviation of the averages.
I'm doing the standard deviation of the samples. So we have sample 1 and sample 2, measurement 1 and measurement 2.
Yeah. So now you just divide that by that.
No,
Minus 0.349.
so these are just the averages of our 10 observations. So this is the standard deviation of our 10 observations.
Oh, I thought that was your average.
That's the average. That's
Okay.
yep. Sorry.
So now we have
I don't know
to
what that do.
minus
I-
one variance to the second variance.
I don't know. I just stand up here and ask questions. So we have the F-test, right? So our F-test is used to compare variances. So we have two data sets, and we want to say, is the variance the same? So we might want to use the F-test, right? Like,
So you have to have 0.349 divided by. But once you
Squared,
start
right?
so the-
I don't know.
Oh.
I
It's
just
a standard deviation of all.
I just stand here and ask questions.
It's only-
Yeah, well, 0.349 squared over
Okay.
275 squared.
So good place to start for doing the F-test is write down the formula for the F-test, right? Probably a good place to start. Well, if you need an even easier place to start, might be with our null and alternate hypotheses, right? So what's our null hypothesis? No. For what we're testing here. So what's our null hypothesis? The thing that we are assuming to be true.
The variations are equal.
Are we comparing the sandwiches now, or are we comparing the difference between our operators? So you versus your friend, right?
Yeah.
Okay, so what are we comparing?
Sample one and
Well, what,
The variance
the variance, there we go. The variance of sample
are equal.
are equal, right? So the variance of your measurements is the same as the variance of your second operator, exactly. Our alternate hypothesis is what?
They're not equal.
Yeah, they're not equal. Okay. So what's our degrees of freedom of our first sample? How many observations do we have in the first sample?
Marcy Carroll.
10.
Okay, so our degrees of freedom is?
6314.
And our degrees of freedom in the second sample?
6314.
Okay. So how do we calculate out our F critical? Well, it's from the F table. Confusing?
Yes.
Okay, that's why we're practicing. Okay, so we have our F table. So we need to know our degrees of freedom of our numerator and our denominator. Turns out our degrees of freedom are the same. In this case, they're both 9. So we read across to 9 and 9, where those two intersect. And what do we get? 3.1789.
And what is that number?
3.1.
F critical.
Yes, our critical value. Okay, so now that we have our F critical value, now we need to calculate our F test. So what does the rule say?
Factor is the large number of dividing.
The bigger one goes on top, the 3, 4, whatever.
So whatever is the bigger one.
Oh, no.
So it's sample 1's on top.
1, 3, 4.
Okay, so our formula is sample 1 over sample 2, right? Okay, but we're doing the square. So what do we have? What is Excel giving us? Is Excel giving us the standard deviation or the variance?
Standard deviation.
Okay, but what's this formula based upon?
Standard deviation squared.
Yeah, which is the variance. Cursor. Okay,
So couldn't you just done 3 point, I don't know what that fancy little formula is you put in there, but
I just did
can't you just do 3 point
that square.
times itself?
Yeah. That's what I did. That times, here's the second power, squared.
Marcy Carroll,
I
please
think the whole
dial
thing goes up.
6314.
Shift 6.
Marcy Carroll,
Shift
6314.
Oh, we learned something new. You can say that we learned 2 things today. Shift 6 is the caret, which is the raised to the exponent, and we learned that Subway might be lying in Eatontown when they say their sandwiches are 12 inches. Okay, so we know S1 squared equals 0.122. S2 squared equals 0.0756. Okay, so what's our F test? One point six three. draw a picture, the F distribution is actually going to shape like that. And we find out that we're in our HO region. The F distribution is actually skewed to the right. Okay. So based upon our F test being less than our F critical, and we go with our null hypothesis, which means what? What's the conclusion that we draw?
That they're equal.
Yeah, that we don't have enough evidence to say that your measurement is statistically different than the measurement of your friend. That the variances or the standard deviations are the same.
They are the same.
Well, we don't have enough evidence to say they're different, so in non-precise language, we can say they're the same. But we actually failed to prove that they're different. Unfortunately, the double negatives in statistics become annoying because there's a technical difference of failing to prove that there is a difference.
So you would say, so therefore you reject the alternate.
Well, we fail to reject the null. So what we're trying to do is we're trying to collect enough data, to collect enough evidence to say that there is a difference. And in this case, we collected our data. There wasn't enough evidence to say there was a difference. And the important conclusion there is just because we didn't find that there was a difference doesn't mean that there's not actually a difference. It just means we didn't find it. It could be because our sample size wasn't big enough. It could be just because we got an unlucky sample. It could be for a lot of other confounding factors. Confounding a word we'll meet with design of experiments, which is some sort of factor that we're not considering that's really influencing our data. So there might be a difference there. We just didn't find it. Okay. Any questions for me regarding hypothesis testing? We'll keep going through it for the next couple of weeks, but it's really important that you walk through the procedure. So you have an 8-step procedure of how to go through hypothesis testing. So become familiar with that. The first is to identify what you're testing and use the decision trees to figure out what population parameter you're testing. So are you testing the mean? Are you testing the variance? Are you testing the standard deviation? Are you testing goodness of fit? Then use the decision tree to determine what test you're using. Then what test you're using, it relates into what table you're using to find your critical values. Also, you need to formulate your null and alternate hypotheses. The null hypothesis being what you assume to be true, the alternate being what you're trying to prove. And your alternate defines, are you dealing with a one-tail or a two-tail test? So just walk through that 8-step procedure, calculate out your statistic, ultimately draw the picture that compares your calculated test statistic to the critical value. And if you're in the shaded region, you go with your HA. If you're in the non-shaded region, you go with HO. If you can do that, you master hypothesis testing.
So here in this case, F value is comparing with the critical.
Yep, you compare the F test to the F critical. Just like in the T test, you compare the T test statistic to the T critical value. So you're always going to compare the value that you calculate out through the formula to the value you get from the table. Cool. I will see you guys next class. Have fun.
You were going to resend us the chart with the page numbers on it, and I left you a Post-it note, and you never did.
I thought someone was going to forward you that, but okay, I'll resend that.
Yeah, no, if you could, please.
Yep, no problem.